Why is critical state soil mechanics key to understanding liquefaction? Imagine a busy city street suddenly turning into a flowing river during an earthquake. That's what happens when soil loses its strength in a process called liquefaction. It's a major concern in areas prone to earthquakes and tsunamis. But how do engineers predict when this will happen? That's where critical state soil mechanics, or CSSM, comes into play. CSSM is a way to understand how soils behave when they are stressed, especially during shaking. Instead of just looking at past cases, it uses scientific principles based on how soils respond to forces. It focuses on two main ideas. First, soils reach a point called the critical state line, where they stay stable under ongoing deformation without changing their volume or stress. Second, when soils are sheared or pushed, they tend to move toward this critical state. During an earthquake, the shaking causes soil particles to shift and rearrange. This movement creates excess pore water pressure, which is water trapped between soil particles. If this pressure gets high enough, it reduces the effective stress that holds the soil together. When the effective stress drops to near zero, the soil behaves like a liquid. This is liquefaction, and it can cause buildings to sink or collapse, roads to crack, and even landslides. CSSM helps explain why some soils liquefy while others don't. It shows how different initial conditions like soil density, stress levels, and particle size influence the response to shaking. For example, loose, sandy soils are more likely to liquefy than dense, clay-rich soils. By understanding these factors, engineers can predict which areas are at higher risk during an earthquake. One of the key tools in CSSM is the state parameter. It measures how far the soil is from reaching the critical state. If the soil is close to this point, it's more likely to liquefy under seismic forces. Engineers use tests like the cone penetration test to measure soil properties in the field. These measurements help determine the soil's current state and its potential to liquefy. CSSM also considers the effects of small particles called fines, confining pressure, and the initial stress conditions of the soil. All these factors influence how the soil will behave during shaking. This physics-based approach is more reliable than just looking at past earthquake records because it uses measurable soil properties. By applying CSSM, engineers can design better foundations and ground improvements to reduce liquefaction risk. They can also develop early warning systems and emergency plans for earthquake-prone regions. In essence, CSSM provides a clear picture of how soils respond under stress, making it an essential tool for understanding and preventing the destructive effects of liquefaction during natural disasters.